Magnetic field force on a moving electric charge. Not only do magnetic poles exert a force on each other, but a magnetic field will exert a force on a moving charge. If the charge is not moving, it does not feel a force. This is a very unique concept and phenomenon in the universe. The force on a moving charge is related to the magnitude of its charge, Q, its velocity, and the strength of the magnetic field, but only the portion of the magnetic field that is perpendicular to the charge's motion. This will become clearer in APC physics, but for now, here's the equation. F is equal to Q times V times B perpendicular. The previous slide gave you the magnitude of the force. Now we want to find the direction of the force. Basically, it's perpendicular to both the direction of the charge's velocity and the magnetic field. In vector analysis, this is called the cross product, or the curl. We're going to use the right-hand rule to find the direction of the force. Now, this is different from the right-hand grip rule that we showed earlier. That found the magnetic field direction to an electric current. This is a little bit different. Step 1. Point the four fingers of your right hand, make sure you use your right hand, in the direction of the charge's velocity. At this point, don't worry whether it's a positive or negative charge. That'll come after step 3. Step 2. Curl your four fingers, it's these guys here, perpendicular to your palm and point them in the direction of the magnetic field. So we have the velocity of the charged particle it's moving, and we have the magnetic field in this direction. And finally, step 3. Extend your thumb perpendicular to your fingers. It is pointing now in the direction of the magnetic force on a moving positive charge. See how all these three vectors are perpendicular to each other. Charge was moving this way, field was coming in this direction, and the force is directed straight up. Now, what would be the direction of the force on a moving negative charge? I told you we would get to that. And what happens if the velocity of the charge is parallel or anti-parallel to the magnetic field? If the moving charge is negative, then the direction of the magnetic field force on the charge is opposite the direction of your thumb. So this is the direction of force on a positive charge. You would be down into the desk there if it were a negative charge. Also, if the velocity of the charge was either parallel or anti-parallel to the field, there is zero force. You can see that from the equation, which is Q times V times B perpendicular. So if it's parallel, there's no force. And frankly, you'd have a hard time having your fingers point in that direction and this direction at the same time. You just can't do it. And if the charge is not moving, then it also feels no magnetic field force. Let's look at the problem now without the hand. We have a negative charge moving this way and a positive charge moving this way with the velocity. The magnetic field, if you'll remember, the dots mean is coming out of the board. Use the right-hand rule to find the force on the positive charge. Then you can use the same rule for the negative charge, but then just flip the direction of the resultant force. So take a second to do that before you go to the next page and see what the answer is. It will take some practice to get your right hand in the right direction for these problems. But here we have a positive charge going this way and the field is coming out of the board. So I already know what to do on this one. So just bear with me. There's your hand, and you've got your thumb over there, and this is the palm of your hand, so the fingernails are on the other side. You'll want to curl your four fingers into the direction of the magnetic field, which is out of the page, and then move your thumb perpendicular. So what you're going to have, your four fingers like that, and then you're going to extend your thumb out like this, and that means the force is in the down direction on a positive charge. For a negative charge, the force is in the opposite direction. So the force on a negative charge would be up. So if we shot a positive charge in here, it will feel a force down, and a negative charge would feel a force up. And then you can remember those curves from kinematics maybe, and from dynamics. When a charge enters a uniform magnetic field, and that's all of this, all the x's, it experiences a force perpendicular to its velocity. In this case, the charge is positive, the field is into the page, the initial motion is to the right, I'm going to look down here, and the force is always perpendicular to the motion using the right hand rule. So let's use the right hand rule down here. You put your four fingers in the direction of the velocity, face your palm into the page, and curl your fingers if you'd like, and then your thumb is pointing in this direction. That tells you the magnetic force. You can do that for all these positions. Let's take this position over here. Four fingers go straight up, palm into the hand, curl your fingers, and where's the force? To the left, just like it shows. What type of motion occurs when a constant force, okay, because we have a uniform magnetic field, is always perpendicular to an object's velocity? We have uniform circular motion. The charge is constantly accelerating perpendicular to its motion, which results in a counterclockwise circular orbit, and the magnitude of the velocity, the speed, stays constant. An electron, which of course has a negative charge, is injected with velocity into the magnetic field as shown here. Here's your electron's initial motion. It will have a magnetic force directed to the right of its path at all times. That'll give you clockwise motion. You can use the right hand rule, and then you'll find that your thumb is actually pointing this way, but since it's a negative charge, you reverse the direction to find the magnetic force. Circular motion was covered in mechanics. Looking at the diagram, can you see the relationship to the gravitational force? This could be a planet moving around the sun. What happens to the speed of the planet as it orbits? Let's assume a perfectly circular orbit. Based on that, predict what happens to the speed of the charged particle in a magnetic field, which actually I said a couple slides ago. For a planet in a gravitational field, the force is always perpendicular to the motion of the planet. Thus, no work is done on the planet and its speed stays constant. Okay, that's of course assuming a perfectly circular orbit. The same is true for a charged particle moving in a magnetic field. In both cases, the velocity changes constantly because its direction keeps changing. Remember, velocity is a vector. It has direction and magnitude, but its speed is constant. At the end of this unit, we'll see a practical use for this. Now let's bring in a horseshoe magnet. If you take a bar magnet and bend it in the middle and make a U shape, you get a horseshoe magnet. And it gives a very nice uniform magnetic field between the two poles, pointing from the north to the south pole. If a charge is injected with a velocity from right to left, it's moving in this direction, it will experience a force away from the magnet, right here. Later, we'll show how this principle can be used in motors and stereo speakers. Example 1. We have a positive charge moving with a constant velocity v, entering a region of uniform magnetic field pointing out of the page. What is the direction of the magnetic force on the charge? Use the right hand rule. Point the four fingers of your right hand, here we have a little model here, in the direction of the charge's velocity, which is to the left. Curl your fingers perpendicular to your palm and point them in the direction of the magnetic field. So that's out of the page. Or you can just face your palm in that direction. Extend your thumb perpendicular to your fingers. It is pointing in the direction of the magnetic force on a moving positive charge, which is up. Answer is up. A proton with a charge of 1.6 times 10 to the minus 19th coulombs, that's the elementary charge E, moving at a speed of 3 times 10 to the 4th meters per second, enters a magnetic field of 0.55 Tesla as shown here. Find the direction and the magnitude of the magnetic force on the proton. Let's start with the magnitude of the force, and we'll use F is equal to QVB. And here's our givens up here. And it's actually, the velocity has to be perpendicular to the magnetic field for this to work, and it does. We've got the velocity coming down here. The field is out of the page, so they're perpendicular. Substitute in our givens, carry out the math, and we have 2.6 times 10 to the minus 15 newtons. We'll use the right hand rule to find the direction of the force. We point the four fingers of the hand down, that's in the same direction as the charge's velocity. Curl your fingers perpendicular to your palm and point them in the direction of the magnetic field, or just face your palm in that direction, and that's out of the page. Then extend your thumb perpendicular to your fingers. It is pointing in the direction of the magnetic force on a moving positive charge, which in this case is to the left. An electron, whose charge is minus 1.6 times 10 to the minus 19th coulombs, has a horizontal velocity of 6 times 10 to the 5th meters per second towards the east. So now you have to know what compass rose, right? North, east, south, and west. And if you take the first letter of each one of them, it spells news. It travels through a 0.24 Tesla uniform magnetic field, which is directed straight down. And this time the down direction is into the page, right? So if you're looking at a map, down is into the earth, so that's why those X's are there. What is the direction and magnitude of the magnetic force on the electron? Let's calculate the force first. So we use force is QVB, where the velocity is perpendicular to the magnetic field, and that's what we have, right? We've got the velocity going this way, and we've got the magnetic field going into the page. Substitute in the givens, and we get the magnitude of the force is 2.3 times 10 to the minus 14th newtons. We're not worrying about the negative sign on the charge. We're just finding the magnitude. The right-hand rule will give us the direction of the force. So point the forefingers of your right hand in direction of the charge's velocity. So that's east, like this. Curl your fingers perpendicular to your palm and point them into the direction of the magnetic field, which is into the page. And then curl these fingers, or just face your palm in the direction of the magnetic field, which we've done, and then extend your thumb perpendicular to your fingers. And your thumb should be in the up direction. But that's not your answer. That would be if it were a positive charge. We have a negative charge. So, since the charge is negative, reverse the direction of the force. So the force is going to be in this direction. And in this problem, that direction is called south.